So here is our high and low pulses on two separate channels. So if you can see here, the top pulse is the high pulse, which measures if each division here is 250 nanoseconds. Then the high pulse measures 1, 2, 3.5, which, measures out to be, let's put the cursors on, and measure it out to be about 805 nanoseconds. And the low pulse is about 1.5 divisions, about 400 nanoseconds. The clock is running at 787 kilohertz at the moment, and it's adjustable. The only problem is that the rise of the leading edge, the front edge of the clock on the low pulse is not synchronized with the clock on the high pulse. And I want them to be synchronized. So I was trying to delay the second circuit, the low pulse one, by a little bit. And I tried to use an inverter chip, this 74HC04, which it's a hex inverter. And the problem is the propagation delay of this inverter is only 15 nanoseconds. So when I inverted it 6 times through all the stages of it, I only got a tiny bit of delay. So instead, I used 2 transistor-based inverters, and you can see them right there. 1 transistor there, 1 transistor there, and it's a 2N2222 NPN transistor. And when I use the transistors to delay the circuits, let's connect this up and see what we can do here. Now I have it connected properly, finally. Sorry it took so long. Now I have it going through those 2 transistor-based inverters. And now, if you could look at the way the signal comes out, the leading edge and the trailing edge, or the leading edge, is now in the right position. The leading edge starts when the other leading edge happens. So, any deviations from this are probably breadboard related, but now you can see it measures about the same. Let me adjust the clock a little bit. There we go. And now we have a high pulse and a low pulse that start around the same time. And the high pulse is exactly what we want it to be, and the low pulse is exactly what we want it to be. And so for the Neopixels, which are a little finicky about the timing, this is going to work out just fine when it gets triggered by the clock. And that should produce the appropriate high and low pulse for the 1 and 0 that we plan on sending to the Neopixels. Anyway, the beautiful thing about using transistor inverters is that they give you a very decent propagation delay. So each 2N2222 transistor, when you add up all the little delays associated with it, including the storage time, the rise time, the fall time, all of that, equals close to about 300 nanoseconds. So by using 2 of them, you get the same signal that's not inverted. Let's get this focused. And you get about a 300 nanosecond delay for each. So the first one inverts it, the second one inverts it again. So you need 2 of them. You need an even number of them in order to keep that low pulse to be the same duration. And you get an effective 600 nanosecond response. And if you can see here, the precise timing required by Neopixels requires 1.25 microsecond period, which, in this case is 1.26 microseconds. Let's get this focused up. All right, so we have here the appropriate size signal, and starting about the same time, and the high pulse measures 805 nanoseconds. If I was going to measure the low pulse here, let me adjust this. Let's see, right there, and this one right there. That measures 405 nanoseconds. And that is exactly what we want. So now, the problem with the TLC 555 timers is that you can't really get a pulse that is shorter than 1 microsecond. And when I'm looking to make a pulse that's 800 nanoseconds and another one that's about 400 nanoseconds, that's really unreliable. So I am going to try to use this as our low and high pulse. In any case, hope this is helpful. The transistor-based inverters are just basically the signal that you're putting in goes into the base of the transistor, and the collector of the transistor is just going to VCC with a 1000 ohm resistor, and the output is coming from the collector side. This is a common emitter, and the emitter is just going to ground. So in any case, thanks for watching. We'll see what happens with the next one.